The level of temperature rise to date, global average 1.35, is already producing the potential of tipping points tipping. We're fooling ourselves if we think we can solve this enormous challenge to a future for humanity simply by reducing emissions. We're fooling ourselves.
Sir David King, we are very pleased to have you with us today, discussing climate repair techniques. Especially, we're talking about the project of Marine Biomass Regeneration. Professor David King is the former Chief Scientific Advisor for the UK government, also founder and chair of the Climate Crisis Advisory Group, as well as of the Center for Climate Repair at Cambridge University. And for decades, you, David, have done extremely important work in climate policy internationally. We will also, as Operaatio Arktis, be joining you and the Cambridge Center for Climate Repair in the next Arctic Circle Assembly in October, which we are very happy about. Which brings us to the interesting topic of 3Rs approach to climate change, which is something that we have adopted also in Operaatio Arktis, and you have, David, done excellent work in describing it. So could you maybe describe what the 3Rs approach means?
Well, thank you, Anton. I'm very happy to do exactly that. My last job in government was my carryover from the negotiations leading up to Paris 2015. And I think it's fair to say that the British government effort was key to getting that agreement on no more than 1.5 degrees. But by 2017, I really understood that 1.5 degrees wasn't the right criterion, as you've just said. We really need to avoid extreme weather events. We need to avoid the perpetual loss of ice from land, which will lead to very high sea level rises globally. And we need to avoid very high temperatures. And this is what we are now experiencing around the world. So what we did was, or I led up the setting up of a Center for Climate Repair at Cambridge, and the objectives were threefold. We're acting as a global hub, a research and operational hub. Right? We're doing the research. We have to do. That's exactly why it's in the university and not standing outside. The first R is reduce emissions deeply and rapidly. Now, quite clearly, we believe that there is no carbon budget left, but we also believe that there is no possibility of having a deep and rapid emissions reduction in a 5-year timescale. Where would that leave the countries that are heavily dependent on fossil fuels for their economic growth, countries like India, countries in Africa, and so on? So we need to see an orderly transition, as orderly as possible, and a fair transition away from fossil fuels, in which the burden, if there is a burden, is carried by the rich world, by the developed world. And we are, of course, frustrated by the fact that that leadership has not been shown to date. We began these discussions in 1992, and here we are still discussing how we can achieve this transition. If I then move to the second R, we believe that the level of temperature rise to date, global average 1.35, is already producing the potential of tipping points tipping. And so if we go straight up to the Arctic region, we all know now that the Arctic region over the last 12 to 15 years has been heating up more rapidly than the global average temperature rise, just over the last 12 to 15 years. And I believe that is strongly correlated with the exposure of the blue Arctic Ocean to sunlight during the 3 polar summer months. And we can all observe that happening on the ice itself. We therefore need to remove greenhouse gases at scale and remove the excess greenhouse gases we have already put up there. Here's the strange thing. Many people believe that greenhouse gas levels were 270 parts per million in the pre-industrial era, which is correct. But if we then look at today, everyone talks about 420 parts per million. That's carbon dioxide alone. If we add in methane, which obviously we should add in, we're well over 500 parts per million already. And there's 10, 15 years ago, there wasn't a climate scientist who believed that we would have a manageable future at over 500 parts per million. So we need actually to bring the level of greenhouse gases in the atmosphere down from the current level, which is about 500 plus, to about 350 parts per million or less, to have a manageable future for humanity. And I say manageable future because sea level rises of 2-3 meters are now scheduled. And beyond that, over the next 100 years, up to 5-6 meters. And that's global sea level rises. We can see all the massive transformation that that would provide. Excuse me. So I think what I'm saying is we're in a very bad place. We have no time to waste whatsoever. In fact, time has shot by. And therefore, we need also a third R, which is really intended to turn time backwards. And so the third R is, let's see if we can keep the North Pole region covered in ice during the 3 polar summer months. Right, so the experiments that we're involved in, and these are global consortia, is to see whether there are techniques that can be operated by us safely that can keep ice covering the Arctic Sea. We know, of course, that in the winter period in the North Pole region, when the sun has gone down to the South Pole, the ice rebuilds across the Arctic Ocean. Can we keep that ice there during the summer period? And that means turning the sun away from the Arctic Ocean, right? And our favorite process is to create bright white clouds covering the Arctic Ocean during the 3 polar summer months. Now there's the answer to your question. I'm afraid it was a fairly lengthy answer, but we are working on, in particular, the second and the third R, because there's a lot more work being conducted elsewhere on the first R.
Thank you, David. That was an excellent answer. And that's also what we are trying to do, to concentrate on the second and the third Rs, because that's such a sort of a way too small discussion at the moment in our society. So thanks for bringing this up. Maybe we then have a few questions on the Marine Biomass Regeneration project, which we found to be very interesting project. So could you just describe the general idea and what it's about and what are the problems it can tackle?
And again, I've got to take a deep breath. I may be a bit long in my answer. So in essence, we know that if we deposit iron on some surfaces of the ocean, we can get phytoplankton formed. And if phytoplankton's formed, this green forest produces an ocean of living matter, living species in the sea. Now, it turns out the experiments that were conducted up to 2010 on ocean iron fertilization produced a whole mix of results. And I think that the reason is because many of the deep oceans are short of other nutrients than iron. And so iron is not the only missing nutrient. And then we discover that whales performed an amazingly important biological pump process in the oceans to keep fertile material in the surface of the ocean. And in the surface of the ocean, it means it's open to sunlight, and that's hence a means of growing a green forest of phytoplankton. And so the story would be that when you get a pod of whales coming up from 300 to 500 meters down below the sea level, and they're orifices are jammed shut by the high pressure of the water. When they come up, it's not only for air, it's also to relieve themselves. So the whale species, it fills the surface ocean, and that can spread, and it can spread over an area of, let's say, 1,000 square kilometers quite easily. And that whole area becomes green in a very short space of time in many parts of the deep ocean. And so what we're looking at is a biological pump action of the whales that has essentially been lost from our ecosystems because we removed the whales in our, you could say, in our quest for oil. Before we discovered oil, we discovered that the baleen whales, the ones that feed 300 to 500 meters down below the surface of the water on krill, that these baleen whales have a large amount of blubber to keep themselves warm when they're down in these cold waters. And so we started catching baleen whales around all of the oceans of the world. And this was very much driven from the United States and from Europe. So we were responsible for bringing the blue whale population down to what is estimated at possibly about 1% of where it was 300 or 400 years ago. So this was a massive operation. And we know when we look at the oil industry, just how these operations work at scale. Once the discovery is made and the finances look good, the boats are developed especially for the process, and soon you're really hunting down the whales all the way down to the Antarctic into the Southern Ocean. And that's where most of the baleen whales are now existing. So what we want to do is to create artificial whale species that we can spread on the surface of the ocean. And we are doing analyses of the missing nutrients in the ocean surface, and we're going to try and match up the artificial whale, I was going to say poo, I should say feces. We're going to see if we can match this up to the missing nutrients in the different oceans that we're working in. Now, it's a long way to go. We've got an experimental operation that will go on for 3 or 4 years, and beyond that, we will extend the process around island nations that are formed by volcanic eruption from the sea floor, so they're surrounded by deep water. These operations can only be conducted in deep water because we don't want any negative consequences, for example, deoxygenation of the water to occur, and this is not going to occur in the deep oceans. So I think the experiments have begun. We have a consortium, and it's composed of universities situated on the coastline of their countries, in India, in South Africa, in the United States. We've got a very good consortium who can work in the major deep oceans of the world. And these experiments will be conducted over the coming 3 or 4 years. The experiments have to check that we do get the growth of phytoplankton. They have to check that we also follow through and get the fish population raised as a result of this. We know that the oceans are still full of fish eggs, even though the abundance of fish in our oceans is massively decreased because we're not covering much of the ocean with these green forests anymore. But nevertheless, female fish lay 100,000 to 200,000 eggs a year. The oceans are still full of them. Most of those, when the larvae hatch, they die. But where there's phytoplankton, that's their food stuff, and they survive. And within a few months, you might have 100 million, even half a billion fish in that area. All right, so the picture that we have is that we are hoping to develop a process that is biomimicry. We want to use natural sources. We want to develop a process that will restore the ecosystems of the ocean, the living population in the ocean, to something where it was 300 years ago. And you know those stories of fishermen going out at that time. The oceans were simply full of fish. They were always confident of feeding themselves from fish. So I think we're first and foremost looking at creating a biosystem that is once again a fully living biosystem. But secondly, yes, we can increase foodstuff for human populations by increasing fish stocks. And thirdly, the capturing of carbon would be very significant. When I say very significant, our best estimate is that once we're rolling this out at scale, and I'm afraid the estimate is very wide-ranging, it's between 3 billion tons of greenhouse gases removed per year up to maybe 13, 14, 15 billion tons of greenhouse gases a year. So once we get a large amount of these ocean green forests going, they will easily compete with the land-based forests of the world.
Okay, that's very exciting. And I think in this matter, if I've understood correctly, this project differs from some other carbon capture ideas in that it could become self-sustaining process. Is that right? Like once you get the life cycle going up and running, it starts to regenerate itself.
That is correct. So we believe that in the process I've described, we will see a return not only of the fish and krill populations, but also of the whale population. And I think it's perfectly feasible to anticipate that maybe in 40 or 50 years' time, that we can leave the whales to do their biological pump action themselves. Right? So it's not as if we would have to carry on in perpetuity. I'll have to carry on to the end of my lifetime, but perhaps not to the end of yours.
Okay, so you said the amount of carbon or carbon dioxide this project could capture is quite huge. Does it mean that before humanity started whaling and fishing on this massive scale, the ocean back then did absorb this much of carbon dioxide, or how is it estimated?
Absolutely. Yeah. That's right. So, I mean, we've taken our eye off the oceans. We're very much aware of the action of deforestation on land, but we haven't focused on the equivalent happening over the deep oceans of the world. And I'm talking about the Indian Ocean, the Atlantic, the Pacific, and the Southern Oceans.
Okay, yeah. So some of the ocean fertilization ideas, projects have been criticized by some people during the years for the uncertain effects of marine life. You already talked about why you do this research on deep sea oceans to avoid the deoxidation problem or whatever it is. But have you identified some major risks in employing MBR in relation to marine life itself?
Yes. I mean, perhaps I should say the most important experiments have been done and are now being doing, and this is what we're doing using satellites. If we examine what is happening in the oceans, for example, we have had two big volcanic eruptions in Vanuatu and Tonga. Vanuatu 2018, Tonga 2021. These were the biggest volcanic eruptions for decades in the whole world. And so we have a paper coming out in which we're analyzing what we can learn from those eruptions. Now, yes, we can see that green matter is formed around these islands after the explosion, just as we would expect from the volcanic dust settling on the surface of the ocean. Volcanic dust has the nutrients required, nitrates, phosphates, silicates, and iron to create this green layer. So it's like a farmer fertilizing the land, right? So we find that, but what is interesting, if we look at fish population, the initial response after the volcano is a reduction in fish populations locally. That's the initial response. And so what we need to do is analyze why this happens. And that's what we're busy doing now. But the interesting thing is, and this is most important, that dip in fish population is followed by a very big rise in the fish population. And I believe, and I've got no real evidence behind this, but I believe this is because of the phytoplankton layer and all of the fish that are living within that layer as their foodstuff. So yes, we need extremely careful work to be conducted, and that is what we're doing. I haven't actually seen any criticism of marine biomass regeneration, but of course there has been a lot of criticism of ocean iron fertilization.
Yes, true. I have the same experience. I haven't seen any specific criticism on this project, but in general, the idea of feeding the ocean with nutrients. But if I've understood correctly, in this project, you are adding also other nutrients than iron and combining them with some like matter, rice husks or something to create a floating.
Yes.
Yeah. Or how does it work?
Right. So basically what you want to do is keep the nutrients in the surface region of the ocean for as long as possible. And the work we're doing up in the Indian Ocean, in fact, it's called the Arabian Sea, is based on the fact that in Goa, India, there's a big rice factory and we can get rice husks free of charge. It's just a waste from the rice factory. And if you bake them at a light temperature, these rice husks float on the surface of the ocean. They're tiny little rafts floating on the surface of the ocean. So the idea is to load these rice husks with the nutrients, and our favorite nutrient at the moment is volcanic dust. So we are collecting samples of volcanic dust. But the nutrients in volcanic dust also contain nutrients that are, contain elements that are not nutrients. And so we have to be careful to see what happens there. By the way, there's a second interesting source of nutrients, natural source, which is desert sand. Desert sand is usually yellow ochre to red colored, and that's because it has a large iron concentration, but again, it has nitrates, phosphates, and silicates. So desert sand has all of the required nutrients as well. So we would like to try desert sand, we would like to try volcanic dust, and we are also then trying to sample these on the rice husks to see whether it improves the generation of the phytoplankton layer. I'm not sure that it's necessary, because if the dust particles are small enough, and this is what happens in natural processes, the surface tension of the ocean keeps them on the surface. Now, of course, if there's a storm at sea, that will mix it into the ocean. But it does mean this is the explanation why these natural processes produce layers of phytoplankton.
Yeah, that's interesting. So, well, good luck with finding the best option for this. My next question is maybe a bit more about economics or politics, I guess. And this is my personal opinion. But one, I think, major problem with carbon removal techniques is that they are quite often used to offset emissions, meaning that they are like a way to make money and way to give companies permission to emit more. So they don't really affect the concentrations of greenhouse gas levels. How do you see these projects in relation to this? And in your mind, what's the ideal way to fund this kind of carbon removal?
You're perfectly right to raise that as a concern, Anton. So I can say that there are several multi-billionaires, well known, I won't name them, who have private jets and who are happy to finance direct air capture processes. These direct air capture processes are very expensive and consume a large amount of electricity, pumping air through a capture device. And maybe $600 a ton. It could be as small as $500 a ton. That's a vast cost. And what they say is it allows me to carry on using my private jet. In other words, the emissions still continue, and we're not reducing greenhouse gases in the atmosphere. So I fully agree with you. That is not the intention. What we need is greenhouse gas removal at scale. And the process you've described is one of the major distortions that the economic market can play on these processes. I think what is also important is to say, many of us, and I used to say this too, believed that carbon pricing was an answer. That's very different from what we were talking about. And carbon pricing was introduced in Britain. I was one of those behind it back in 2003, and then across Europe in 2004. And we all have a carbon pricing system. And the idea was to make incentives for people to stop using fossil fuels. The total carbon price is now no more than $50 a ton in Europe. And it has a fairly small effect on the cost of fossil fuels that people are using. But look at the effect of the Russian-Ukraine war today. Suddenly, the fossil fuel energy prices have gone up a massive amount, but people are still using them, right? So the use is really related to what people conceive as an important part of their lifestyle. Now, obviously, people are faced with poverty now, but nevertheless, I'm just pointing out carbon pricing alone is not the way forward. We need proper regulation and obligation to manage this switch away from fossil fuels. And I don't think too many countries are in the right place at the moment in attempting to get there. Could be zero.
There's this a quote about how much time we have left, and this is like an interesting topic. A lot of activist groups have now adopted a quote from you stating that we have some years, maybe 3 to 4 years left to determine the future of humanity. And as far as I've understood correctly, you were talking about exactly the comprehensive strategy to tackling climate tipping points and climate repair, like refreezing and removing and repairing and reducing and all of this. But still, the emission cuts are the only thing people are talking about, and a lot of also the civil society is talking about only the emission cuts. So what do you think about, should we actually talk much more about these other R's also?
No question, no question. I mean, we're fooling ourselves if we think we can solve this enormous challenge to a future for humanity simply by reducing emissions. We're fooling ourselves. And there's no evidence that supports that today. If we had started this in 1992, when the international discussions began, we would have managed it just by reducing emissions. But now we put too much stuff up there, right? So I think the answer is we need all 3 R's. We need all countries to understand that this is the way forward, and we need civil society to understand this. Governments respond to civil society in democracies, I should say. Now,
absolutely, yeah.
When I said 4 years, if I could just say, I was talking about getting everything in place so that every country can see what needs to be done and can begin to take decisions that take us in the right way. I'm not saying we can solve this in 3 to 4 years, but we need to move the whole process into a situation where we acknowledge this is the biggest crisis humanity has ever had to face up to. And is humanity smart enough to do that? That's the question.
Absolutely agreed. Yes, that's the question. We have just one quite like climate science question left here, which is about the question of committed warming. And this is like one of the big debates in climate science and policy. The question of how how much we have so-called committed warming already because of the greenhouse gases we have in the atmosphere. And some studies say there's virtually none, and they only account for CO2, and they sort of like omit other forcers from the models, and some others which take account all of the gases say there is some, but the amount is uncertain. What's your opinion or your view on this matter? How much we might have warming already? Like if we consider just imaginary scenario where we stop emitting everything right now.
Okay, let's suppose we stop emitting everything tomorrow.
Yeah.
Right. What will happen as we move into the future? Now, clearly, it's going to be better than if we continue emitting 40 billion tons of greenhouse gases, including methane, into the atmosphere every year. But it's not going to stop the crisis emerging. And the reason I say that is because the ice on Greenland is now beginning to melt irreversibly. And the reason the ice on Greenland is beginning to melt irreversibly is because Greenland is now sitting in a blue sea during the 3 polar summer months. And so the loss of ice from Greenland, eventually sea levels would rise globally by 6.5 meters. And nobody would say that is going to be a manageable future for humanity. So I think we need to look very, very carefully at the tipping points, and nobody who talks about the future being safe if we just stop emitting takes account of tipping points. I mean, there are 15 tipping points that the scientific community have delineated. There's going to be a big conference in Exeter later this year on tipping points. And in essence, we're saying the first of the tipping points is happening around the Arctic Circle region, hence this sudden deviation of the temperature in the Arctic Circle from the temperature in the rest of the world. And if I then say, okay, what about just the Arctic Circle tipping point? Does that affect any of the other tipping points? It certainly does. These tipping points are like a bunch of dominoes. One starts tipping and the next one will start going. There's a whole series of these domino effects in these tipping points. So let me say a little scientific point. If you dilute the level of salt in the oceans, then the overturning current that keeps the north part of the world, our part of the world, warmer, this overturning current coming up around Africa from the equatorial region. For your information, these are Greek army jets trying to put fear in the hearts of the Russians and the Turks. So, yeah, strange world. So, where was I? Can anyone remember what I was saying?
About when the overturning current of the
yes.
Atlantic
Okay, so
might
this
slow down.
overturning current, it overturns in the sense that the current comes around Africa and up into the North Pole region, bringing very warm water across from the equator, but also cooling the equatorial region. It's managing the temperature of the world in a very real sense. And this overturning side of it is the current. When the water gets cold in the North Pole region, it gets heavy and it goes down and comes back underneath the top current. So this overturning current is operating like this. Goes all the way around to India, and it keeps the equatorial region cool by taking the high temperature away, and it keeps us warm. It's based on the salinity level of the oceans. And if we dump a lot of fresh water into the Atlantic, the North Atlantic, that will slow down the overturning current. And that's exactly what we're doing. As we lose Greenland ice, we can anticipate the loss of the overturning current. Now that's just one example of the way the tipping points actually tip at each other. So if we take account of all that, I think the future looks very gloomy for humanity. I think we really have to do considerably more now. It means we do have to focus on repairing those parts of the climate system that seem to be breaking. Now, if somebody said to me, how do you repair the overturning current? The answer is, I have no idea. The only way I think we can stop it is by doing that piece of work in the North Pole region to keep the ice covering the Arctic Sea. Okay, well, it's good to meet you all, and I hope to meet you in person.
Yes, okay. Well, have a good day.
Thank you so much.
Bye.
Thank you.